So repeatability of an instrument is the degree of closeness with which a measurable quantity may be repeatedly measured, right. So we go to the next one, which is resolution. This is also very, it says that how much of change in input will actually cause a detectable change in the output. So what is the smallest change in the input? So can we detect a change of 0.1 degree centigrade, or can we detect a change in 0.01 degree centigrade? For example, if you have a clinical thermometer, then you cannot possibly detect a change of 0.01 degree centigrade or 0.01 degree Fahrenheit. Generally they are calibrated in terms of Fahrenheit. So that is the resolution. If a temperature transducer is resolution is 0.2 degree centigrade, then it is the smallest temperature change that can be observed. Okay. Similarly, we have, similar to the concept of dead zone, sometimes sensor systems will have dead zones. For example, we often find that these electrical meters, sometimes they will stick. Any mechanical arrangement tends to develop something like a static friction, which also depends on many things like temperature, time, humidity and other things. So what happens is that till say if you have an ammeter, then till you send a certain amount of current, the torque is not enough to overcome static friction, so the needle doesn't move. So dead zone is the largest value of the measured variable for which the instrument output stays 0. So from 0 to that value there is going to be no deflection, no reading, nothing. So that's called a dead zone. So what's the difference between the dead zone and the resolution? Dead zone is actually the resolution from 0, while resolution can be resolution from 24 to 24.1, 24.1 to 24.2, while generally dead zone is referred to from 0. So it occurs due to factors such as static friction. Similarly, sometimes we have hysteresis in instruments, so that if we have an increasing sequence of input values, if we are increasing the input from, let us say 0, 10 degree centigrade, 20 degree centigrade, 30 degree centigrade, they are increasing sequence of values, then we get one set of readings, while if we have a decreasing set of values, then we get another set of readings, and these readings are distinctly different, right. So in that case we say that the instrument has a hysteresis. It can occur due to various factors like gears, gear backlash, or it can occur due to magnetic components, or sometimes due to hysteresis which occurs due to elasticity. So due to such things the hysteresis can be there. So so this is the figure that we are saying that if x is increasing, then the readings that we obtain follow this curve, while if x is decreasing, they actually follow a distinctly different curve. So if such behavior is demonstrated by an instrument, it is said to have hysteresis. So next, now the errors that we have, so we have actually typically an instrument is supposed to have a calibration curve, but the reading that it has may not exactly match with the calibration curve. It is, if you read out an ammeter, then it has some scale fixed, but if you send exactly 1 ampere current, then the needle may not stand at 1 ampere. So this is the error. Now the error is typically characterized as into two different kinds. So since the instrument is actually assumed to be a linear instrument, so it is assumed that the error can be of two types. The first type is called bias or offset, which is a constant error which is going to stay throughout the range. So maybe when you have an actual current of 2 amperes, your reading shows 2.5. When you have 3 amperes, it shows 3.5. When you have 10 amperes, it shows 10.5. So you have a 0.5 ampere of bias, right. If you see ammeters, normal ammeters, you will find that such biases can be corrected by screwdrivers. They are also sometimes called zero adjusts. Similarly, there can be a gain error. So you have a sensitivity, while we have a nominal sensitivity which is indicated by the scale, and your actual instrument sensitivity may actually deviate from that, and then you have a sensitivity or gain error, and the error in reading due to this gain error is going to be proportional to the reading. So if you are measuring 10 degrees centigrade, then the error due to gain error is going to be half of what you measure due to when you measure 20 degrees centigrade. So we assume that the errors are of two kinds, and these typically in typical sensors and instruments, very often they can be corrected by electronic signal conditioning means. So that's what is depicted, that if you have a zero error, so that's a bias, and if you have a slope error, that's your gain error. Next is drift. So sometimes what happens is that even if you correct at some point of time during calibration, even if you correct for the bias and the gain error, you have drifts in the bias and the gain. So again, such bias and gain errors can develop due to variations in temperature, variations in time, or some other conditions. So the rate at which these will develop are characterized by a performance characteristic called drift. So typically drift is characterized for temperature and time. Now we come to, so this more or less completes our static characteristics. So generally talks about an input output curve, right? That is a calibration curve. So there is no time here. If we give an input, we will get an output in the steady state, and we are only talking about the characteristic between this input and the steady state output value, right?